Julia was built for scientific computing. But what exactly is scientific computing? By the end of this video, you'll know what scientific computing is. And if you're a scientist, you'll know why you might want to consider including scientific computing as part of your discovery process. More specifically, you'll know why you might want to consider using Julia for your scientific computing needs. As a disclaimer, I am not a scientist, nor do I work for Julia. I'm just someone who enjoys learning new things, and someone who enjoys making videos here on YouTube. So what makes Julia so well suited for scientific computing? Well, let's find out. Welcome to Doka.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. This series is intended for intermediate users of the Julia programming language. You don't need to be a scientist in order to watch this series, but I am assuming that you already know the basics of how to write code using Julia, and that you know how to use Julia for data analysis and data visualization. I'm also assuming that you're comfortable using Julia in both VS Code and Pluto notebooks. If you're new to Julia, I would recommend watching some of my other series before watching this series. You can view all of my series by clicking on the tab labeled Playlists. Specifically, I would recommend watching Series 1, which provides an introduction to Julia for beginners, Series 2, which provides an introduction to data analysis and data visualization using Julia, Series 5, which provides an introduction to machine learning in Julia, and Series 7, which provides an introduction to differential equations in Julia. With that said, let's get started. If you do an internet search for "what is science," you'll get all sorts of articles that attempt to answer this question. Let's start with a Wikipedia article on science. Just so we're all on the same page, for the most part, I'll just be quoting directly from this article. Science is a systematic endeavor that builds and organizes knowledge in the form of testable explanations and predictions about the universe. So science is a process that human beings have come up with to answer questions that don't currently have answers, so that we as a species can continuously add to the collection of human knowledge. Science avoids the supernatural and metaphysical realms by sticking to questions that can be tested through experiments and/or observations. Science is as old as humanity itself, and it covers a wide range of disciplines. Modern science is typically divided into three major branches: natural sciences, which study the physical world; the social sciences, which study individuals and societies; and the formal sciences, which study formal systems governed by axioms and rules. Natural science is the study of the physical world. It can be divided into two main branches: life science and physical science. These two branches may be further divided into more specialized disciplines. For example, physical science can be subdivided into physics, chemistry, astronomy, and earth science. Modern natural science is the successor to the natural philosophy that began in ancient Greece. Social science is the study of human behavior and functioning of societies. It has many disciplines that include, but are not limited to, anthropology, economics, history, human geography, political science, psychology, and sociology. Formal science is an area of study that generates knowledge using formal systems. A formal system is an abstract structure used for inferring theorems from axioms according to a set of rules. It includes mathematics, systems theory, and theoretical computer science. The formal sciences share similarities with the other two branches by relying on objective, careful, and systematic study of an area of knowledge. They are, however, different from the empirical sciences, as they rely exclusively on deductive reasoning, without the need for empirical evidence to verify their abstract concepts. There is disagreement whether the formal sciences are science disciplines, because they do not rely on empirical evidence. Applied sciences are disciplines that use scientific knowledge for practical purposes, such as in engineering and medicine. The applied sciences are often contrasted with the basic sciences, which are focused on advancing scientific theories and laws that explain and predict events in the natural world. So the term science covers a lot of different disciplines, and there's some debate as to whether or not some of these disciplines should fall under the science umbrella. Rather than getting into that debate, for the purposes of this series, I will be including every discipline that falls under natural science, social science, and formal science. That includes both basic science as well as applied science. So now that we have an idea of what disciplines are included in science, let's explore how big the global science community is today. So how many scientists are there in the world? According to the 2021 UNESCO Science Report, there were approximately 8.9 million full-time equivalent researchers in the world in the year 2018. As a side note, if you have 2 part-time scientists that are each working 20 hours per week, that equals 1 full-time equivalent. That means that the actual number of scientists is larger than 8.9 million. So that's a lot of people. It's a lot more than I was expecting. Now, how much money is being spent to fund the research activities for all of these scientists? According to a 2022 report by the nonpartisan U.S. Congressional Research Service, global spending in research and development in the year 2020 was estimated to be roughly $2.4 trillion US dollars. This figure includes funding from both public and private sources. $2.4 trillion is a lot of money. Again, this is a lot more than I was expecting. Now, let's say, for the sake of argument, that there are 10 million scientists in the world, which includes both full-time and part-time researchers. Then that $2.4 trillion equates to roughly $240,000 per scientist. After you pay for wages, there isn't much money left to pay for experiments. I don't know the actual split by scientists, but it wouldn't surprise me if 80% of the funding is going to just 20% of the scientists. If that's true, then that would imply that most scientists around the world are severely underfunded. I'm not sure if that is true, but that's what these numbers suggest. If you're a scientist, let me know your thoughts in the comments below. Is this consistent with your experience? Or am I missing something? So despite the trillions of dollars being spent on R&D every year, there doesn't appear to be enough funding to support every scientist in the world. That means that if you're a scientist in that 80% that isn't receiving major funding, you're probably in a hyper-competitive environment with constraints on both time and money. Back in the quote-unquote good old days, there weren't that many scientists in the world. But those few scientists had the luxury of both time and money, either because they were independently wealthy, or because they were tenured professors at research institutions that could afford to fund both their living expenses as well as their research activities. Unfortunately, in today's modern era, the situation is reversed. Today, there are plenty of human resources in science, but there's never enough time or money. Again, I'm not a scientist, but to an outside observer like me, this doesn't exactly sound like a healthy environment that's conducive to exploration. If you need to spend a lot of time competing with your peers to secure funding in order to survive day to day, then your brain is less likely to be in a frame of mind to uncover the next big breakthrough. Of course, I don't know what the solution is, so I'll leave it up to other, more qualified individuals to propose potential reforms for the R&D world. What I do know is that as a scientist, it might be beneficial to consider taking advantage of any resource that may free up some time and allow you to operate in a world of limited cash. Scientific computing is one such resource. Historically, the pursuit of science meant 1. Developing theory, and 2. Conducting experiments and/or observations. With the advent of computers, scientific computing now represents the third leg of the stool in the scientific world. In the early days, scientific computing meant running very large, complex numerical calculations on a supercomputer. A supercomputer is basically a massively parallel computer with extremely fast network connections that's enclosed in a climate-controlled environment. Supercomputers were first introduced in the 1960s, but despite the increasing number of supercomputers around the world, not everyone has access to one, so it remains a niche market targeted at the world's top scientists. But as desktop and laptop computers have become more powerful and networked, it is now possible for just about anyone to perform scientific computing from the comfort of their own home. And because a scientist can now perform scientific computing on a desktop or laptop computer, scientific computing covers a much wider range of subjects than simply number crunching on a supercomputer. Scientific computing is not meant to replace either theory or experiments. You still need both. The motivation behind scientific computing is to complement both theory and experiments, with the ultimate goal of leading to discovery. Scientific computing is not a substitute for physical experiments or human observations. But there are several reasons why scientists may find it beneficial to consider the use of scientific computing as part of the discovery process. Perhaps the system in question moves too fast, or too slow. Or perhaps the system in question is too large, or too small. Or perhaps the system in question is too unstable and potentially dangerous. Or perhaps the required experiments are too expensive to run multiple trials. You get the idea. All of these situations represent constraints in a resource-constrained research environment. Fortunately, many of these systems can potentially be modeled and simulated through the use of scientific computing. Scientific computing gives the scientist a fast, safe, resource-friendly way to aid in the discovery process. But the coding required for scientific computing does take more time to learn, since the software needed may not exist off the shelf. This may require the scientists to create their own software that's domain-specific, or even experiment-specific. I am repurposing this diagram that I used in a previous video. This diagram represents the different tiers of users of a computer programming language. Users at each tier have a different motivation for using a programming language. The motivation of a doer is to keep an operation running. The motivation of a maker is to develop a product or service, often for profit. The motivation of an analyzer is to offer advice to a decision maker, like a business manager or a public policy maker. And the motivation of an explorer is to discover something new, in order to add to the catalog of human knowledge. Scientific computing is part of the explorer tier. But as you can see, it sits on top of all of these other tiers. So in order to perform scientific computing, the scientist also needs to have some knowledge of everything below it. So if you're new to programming and new to Julia, this is why I'm suggesting that you watch some of my other series before you watch this series. In order to pursue scientific computing, you need to have some knowledge about how computers work, some knowledge about software development, and some knowledge about data analysis and data visualization. That's a big investment in time. That's in addition to the investment in time required to become an expert in your particular scientific domain. I say this knowing that scientists don't have time to spare. I'm not saying this to scare you away. I'm saying this to set some realistic expectations when it comes to learning scientific computing. Like many things in life, in order to save some time in the future, you need to invest some time up front. Once you've decided to take the plunge and pursue scientific computing, the next question is, what programming language to use? When considering various scientific computing languages, at some point you will no doubt encounter a language called Fortran. Fortran is the oldest programming language that's still in use today. There's some debate as to what Fortran stands for. Depending on the source, Fortran may be short for Formula Translating System, Formula Translator, or Formula Translation. But there's no question that Fortran was invented at IBM by a team led by John Backus. Fortran was initially released in 1957 and was intended for scientific and engineering applications. The latest stable release is Fortran 2018, which was released in the year 2018. Among other things, Fortran code is still used today to benchmark the performance of the top 500 supercomputers around the world. If you do an internet search for Fortran, you'll come across several articles that asserts that Fortran is the dominant language of scientific computing, but it's difficult to find any usage data on Fortran. For example, this Wikipedia article on computational science asserts that, historically and today, Fortran remains popular for most applications of scientific computing. This quote is accompanied by 2 footnotes, neither of which provides any data regarding how such a claim can be made. If you look at Google Trends, you can see that searches for Fortran have been declining for decades. In the January 2023 TIOBE Index, Fortran's rank is essentially the same as Julia's rank, which leads me to wonder how many scientists are still using Fortran today. If you're a scientist, let me know in the comments below. Are you using Fortran? In any event, I think it's safe to say that Fortran hasn't had a serious competitor in the scientific computing space until Julia was released to the public in 2012. Since its release, Julia has made significant gains within the scientific computing world. A lot of articles online like to compare and contrast Julia to Python or C or C++. But in many ways, Julia is the spiritual successor to Fortran. Julia was created specifically for scientific computing, so if you're a scientist, then Julia should definitely be on your list of languages to consider. Conceptually, Julia offers scientists the high-level prototyping capabilities of Python, while retaining all of the low-level speed and number crunching capabilities of Fortran. This allows the scientists the ability to quickly test out multiple hypotheses, so they can focus on only the most promising ones. The fast speed allows the scientists to run through simulations quickly, without having to change languages. Or alternatively, if time is not the bottleneck, then Julia Speed allows the scientists to run more sophisticated simulations within the same amount of time. The subject of scientific computing is a vast field that is still evolving, so I will only be able to introduce a limited number of subjects. Over the next few weeks, I hope to introduce such topics as parallel computing, differentiable computing, and probabilistic computing, none of which will be domain-specific. This series won't turn you into a scientist, but it will introduce you to some of the concepts of scientific computing so you can get started down that trail. This should be a fascinating adventure, so I hope you'll join me on this path to discovery. If you made it this far, congratulations! If you enjoyed this video, and you feel like you learned something new, then please consider smashing that like button, leaving a comment, sharing this video, and subscribing to this channel. If you'd like to support the educational work that I'm doing, then please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get ad-free early access to all of my new videos. Thanks for watching, and good luck on your Julia journey.